Hey everyone, and welcome. If you're cramming for a quiz, working on a project, or you're just curious about polar coordinates, you have come to the perfect place. In this study session, we're going to break down everything, from the core ideas all the way to the Python code you'll need to really get a handle on this. So let's dive in.
We're all super comfortable with the classic XY coordinate system, right? Go over some amount, go up some amount. And it's fantastic for anything that fits on a grid. But what happens when you're dealing with circles or spirals or anything that rotates? Things can get kind of messy. What if there were a better, more elegant way to describe those kinds of shapes? Well, there is, and it's called the polar coordinate system.
Okay, so here's our game plan for today. We're going to start with the absolute basics. What even are polar coordinates? Then we'll get into the nitty-gritty of converting between polar and Cartesian. After that, the fun part. We'll start visualizing things by graphing polar equations in Python. We'll even touch on a cool calculus application, and we'll wrap it all up with a set of final study notes so you can ace this topic.
All right, let's jump into our first section. The big idea here, it's all about a mental shift. Seriously. Instead of thinking about left-right, up-down on a grid, we're going to start thinking in terms of circles and rotation. It's a whole new way of describing where a point is based on its distance from the center and its angle. This slide just lays it out perfectly. On the left, you've got Cartesian. You get to a point by walking along the x-axis, then making a 90-degree turn and walking along the y-axis. But on the right, with polar, it's totally different. You stand at the very center, you turn a certain angle, theta, and then you just walk straight out for a distance r. It's just two different sets of directions to get to the exact same spot. So let's nail down what these two parts mean. First, you've got r, the radius. It's super simple. How far is the point from the dead center? The origin. That's it. And then you have theta, or theta. That's your direction. It's the angle you turn, always starting from the positive x-axis and going counterclockwise. So remember, distance and direction. That is the polar pair.
Okay, so knowing both systems is one thing, but where the real power comes in is being able to translate between them. This section is all about that. It's the bridge, the mathematical Rosetta Stone that lets us connect the world of XY with the world of r theta.
So going from polar to Cartesian is really just some basic high school trig. If you imagine a right triangle where r is a hypotenuse, well, the adjacent side, your x value, is just r times the cosine of theta. And the opposite side, your y value, is r times the sine of theta. And look at the Python code. It's literally a one-to-one translation of those formulas using the built-in math library. Super straightforward.
Now, going the other way from xy to r theta is just as easy. To get the distance r, we just use the Pythagorean theorem, and you can see the source code uses this really slick function, math.𝑦, which does that for us. For the angle, theta, we use the inverse tangent. But, and this is a huge pro tip, notice the code uses math.𝑎 tan2 of y, x. You'll want to use this one because it's way smarter. It looks at the signs of both x and y to put your angle in the correct quadrant, which saves you from all sorts of weird bugs.
All right, now for my favorite part, where the magic really happens, visualization. We're going to stop talking about abstract points and actually use Python to turn these equations into some incredible and often really beautiful shapes. This is where you really see why polar coordinates are so cool. So before we jump into the code, here's a little preview of what's coming. It's amazing how simple polar equations can create such complex shapes. Just setting r to a constant, boom, a perfect circle. Start throwing in sines and cosines, and you get these incredible rose curves and limicons. They look like flowers or hearts. Add an exponent, and you get a perfect spiral. Let's actually plot a few of these. Okay, our first example is a special kind of limicon called a cardioid, because, it looks like a heart. You get this shape when the two numbers in the equation are equal, like they are here, with 2 and 2. Just think about it for a sec. As the cosine of theta swings from +1 to -1, the radius r smoothly shrinks and grows, creating that perfect little pinch at the bottom of the heart. The code is super simple. We use NumPy to create a bunch of angles, calculate r for each one, and then tell matplotlib to plot it. Next up, the beautiful rose curve. The general formula has that n inside the cosine. In our case, n is 5. And here's a super neat trick with these. If that n value is odd, the flower will have exactly n petals. So since n is 5, we get this perfect 5-petaled flower. The code is pretty much the same as before, we're just swapping out the formula for r. And for our last one, the spiral. And believe it or not, this one might have the simplest equation of them all. The radius r is just directly proportional to the angle theta. So as our angle sweeps around and around, the radius just keeps getting bigger and bigger, drawing out this perfect ever-expanding spiral. You'll notice in the code, theta goes all the way up to 4π. That's 2 full rotations, which gives the spiral enough room to really take shape.
Okay, let's switch gears a little bit. We've seen the pretty pictures, and now let's look at a more advanced application, calculus. And don't worry, you're not going to have to do any integrals by hand. We're going to see how a really powerful Python library can do all the heavy lifting for us, making a tough problem surprisingly easy.
So this formula right here is the key to everything. To find the area of a shape made by a polar curve, you integrate 1/2 of the radius squared over your angle, theta. The best way to think about it is like you're adding up the areas of an infinite number of teeny tiny little pizza slices to get the total area of the whole shape. And here is how we make Python do the work. We use a library called 𝘄𝘄𝘄𝗋, which is built for symbolic math. It thinks in terms of equations, not just numbers. So step 1, we tell 𝘄𝘄𝘄𝗋, hey, this theta thing, it's a symbol. Treat it like algebra. Then we defined our R equation using that symbol. After that, we just build the area expression right from the formula we just saw. And for the final step, we tell 𝘄𝘄𝘄𝗋 to integrate that expression, and we give it the bounds from 0 to π/2, which traces out exactly 1 petal of the rows. 𝘄𝘄𝘄𝗋 handles the whole messy calculus part automatically. It's awesome.
And boom, there's our answer. 𝘄𝘄𝘄𝗋 crunches through the calculus and gives us a precise number for the area of one of those petals. This just goes to show how you can go from a complex mathematical formula to a concrete numerical answer with just a few lines of code.
Whew, we have covered a lot of ground. We went from basics theory to plotting code to symbolic calculus. So now let's just boil it all down to the absolute must-know essentials. If you're studying for a quiz, seriously, this is the slide you're going to want to screenshot. These are the key takeaways.
Okay, let's recap. First, the absolute core definition. A polar coordinate is just a distance r and an angle theta. That's it. Second, know your conversion formulas cold, both ways. And remember those helper functions in Python, 𝘄𝗋 and especially atan2. And third, know your toolkit. You've got NumPy for all the heavy-duty math, Matplotlib to make the beautiful plots, and ∑ for when you need to do some calculus. If you can nail these points, you're going to be in fantastic shape. And I'll leave you with this final thought, just to connect all this math back to the real world. We saw how a dead simple equation, r equals theta, creates a perfect spiral. So start thinking, where do you see spirals in nature? In seashells, the arms of a galaxy, the seeds in a sunflower? What does that suggest about the simple underlying mathematical rules that might be governing how these things grow? Thanks so much for joining this explainer, and good luck with your studies.